Hello everyone. Today let's solve the problem. One second. New year and permutation concatenation. Right. So this was asked in the this one. It says goodbye 2018 here. So basically this was asked in something which was related to the division 2. Right. So it says goodbye 2018 here. Right. So Codeforces round which was asked for the division 2 mainly. Right. So you can just go through the question. It's very easy to understand, man. Right. It's very easy to understand. Let's do one thing. I'll just summarize the question so that it will be easier for us to solve the problem, right? So we have to count the number of contiguous subarrays of length n. What we need to do here, just give me a second. We have to count the number of contiguous subarrays of length n, right? What we need to count actually, we need to count the number of number of contiguous subarray. I'll just write here contiguous subarray. I'll just write SA, right? Of length n in the concatenation of all the permutations from 1 to n, right? So again, so we have to count the number of contiguous subarrays of length n in the concatenation of all the permutations of 1 to n listed lexicographically, right? Whose sum equals n into n plus 1 by 2, whose sum equals n into n plus 1 by 2, right? So this one I'm speaking of. Right, so we have to count the number of contiguous subarrays of length n in the concatenation of all the permutations of 1 to n listed lexicographically whose sum equals n into n plus 1 by 2. So this part is very important. The big sequence length is n into n minus 1. The big sequence length is nothing but n into n minus 1. Right, so we have to output or yeah, we need to output the count modulo. This one they have given here, 9982444353. This is like a phone number, man. Yeah, this is fine. So we have to output the count modulo 9982444353, right? And given n 1 less than or equal to n and n is less than or equal to 10 to the power of 6, right? So this is the constraint they have given, right? We have to compute the count. Again, the modulo value we have to make use of this one, right? So we have to count the modulo 9982444353. So this is important as well. So mainly what we need to count, basically we have to count the number of contiguous subarrays of length n in the concatenation of all the permutations 1 to n, right? And whose sum is equal to n into n to the power of 1 by 2. That's what we need to do. We have to count the number of contiguous subarrays of length n. That's what we need to do, right? And also we need to keep in mind that the big sequence length is n into n factorial. So sorry, this is not n into n minus 1. So I have written wrong. Let me got this one. Sorry for this. This is actually, basically I can write in this way. Let me write this one as n into n factorial. This one, right? So this is just n into n factorial, right? The big sequence length is n into n factorial. We have to output the count modulo this one they have given here, 9982444353, right? So given n, the constraints are 1 less than or equal to n and n is less than or equal to 10 to the power of 6. We have to compute the count, right? So simple one. This is very simple one. Let me remove this one. Let me come to the input output part here. So n we have been given 3, right? N we have been given 3 here. So we have to compute the count, right? So we have to compute the count here. The count is 9. The count is 9. Same goes with this input as well. This input as well. So we have to consider the modulo value, count modulo value. So this one is very important, right? Whatever the value they have given, 9982 44353. So this one we have to consider. So this is just the input output part I wanted to this one consider. So now we are done with the question as well as the input output part. Let's do one thing. Let's go with the let's discuss the approach followed by the complexity, and then let's write the code. Initially, as usual, let's discuss the approach first. So now let's consider the same first example that they have given in the example. I'll be considering the same thing for the approach. So now I have considered the first example as I have said, right? So the output that we need to get here is 9, right? So we will be going with the DP approach, or we will be going with the dynamic programming. Just keep this on Right. Let's move on with the step-by-step explanation here. First thing, before getting into step-by-step explanation, I have considered the same first example 3, the output that we need to get here is 9. So before getting into the step-by-step explanation, so we in the question, I had read this one out loud. Basically, I had explained this one as well. So sum of 1 to I, nothing but here, sum of 1 to I, right? So this one, sum of 1 to I, this is nothing but n into n plus 1 by 2 we went, right? So when we are considering in the um, I format, we have to go with I plus 1 by 2, I into I plus 1 by 2, right? So we will be going with dp of I equals nothing but number of length minus I subarrays with a sum s, right? That is in the concatenation of all the permutations 1 to I. So and factorial of I equals I factorial, nothing but mod m. So this we had discussed in generally basically in the question, right? So now we are going with I into I by 2, and dp of I is nothing but number of length minus I subarrays with the sum s in the concatenation of permutations of 1 to I, nothing but number of length minus I, and factorial of I equals I factorial, right? So that's it. You have to remember these two, right? So first what we'll be doing, we will be listing all the permutations, man. We have to list, or we will be listing all the permutations lexicographically, right? So in the question they have asked lexicographical itself. um, so we will be listing permutations lexicographic and going with the, and we'll be going with the concatenation p, right? So permutations of 1 to 3, so we have to consider all the permutations from 1 to 3, means 1 2 3 are the numbers, right? So there are 6 permutations here. See, 1 2 3, 1 3 2, 2 1 3, 2 3 1, 3 1 2, and 3 2 1. So these are the 6 permutations we are going with for from 1 to 3 as n equals 3, right? As n we have been given 3, we will be going with a permutations of 1 to 3, because we are listing the permutations in the lexicographical order. So 1 has to come first. So n we have been given 3, so we are going from 1 to 3, right? So this is very easy to understand, fine. And we have to go with the concatenation of p as well, right? So let's concatenate here. So this will be 1 2 3, 1 3 2, 2 1 3, 2 3 1, 3 1 2, 3 2 1. So see here, these consist of the different arrays, right? So now we are concatenating, now we are removing the thing, and we are just concatenating. This one will be 1 2 3, 1 3 2, 2 1 3, all the numbers, man, all the six, all the numbers present in these six this one permutations, right? So this is fine, I guess, right? So let's move on with the second step here. So now first let's go with base nothing but I equals 1. We have to go with I equals 1, I equals 2, and I equals 3, right? In the form of iterations we can go, right? So here dp of I equals 1, first thing, yeah, this I equals 1 base value, dp of I equals 1, and factorial of 1 is 1 factorial nothing but 1 itself, right? So dp of I is 1, factorial of 1 is 1 for the base I equals 1. Next let's go with I equals 2. Means we have to build I equals 2. Permutations are only two numbers we are considering, 1 comma 2 and 2 comma 1. These are the permutations, right? Concatenation, when we concatenate, this one becomes 1 2 2 1, right? So we are just removing the array here. When we concatenate both, we get 1 2 2 1, right? So the formula we had went with, if you remember, so length minus 2 here, because I is 2 here, right? So this one will be going with the windows in the form of sliding window, man. 1 2 sum 3, right? 2 2 comma 2 1, right? Sum 3, this is equal to 2 windows, right? So these are the two. See here, 1 2 sum 3, 2 2 comma 2 1, these are the two windows, right? Sum 3 equals two windows, right? So just keep this in mind. Now we will be going with the recurrence numeric check. Recurrence numeric check, nothing but here dp of 2 equals 2 into dp of 1 plus factorial of 1 minus 1. So dp of 1 is 1, we know this one, right? So initially I equals 1, right? dp of 1 factorial of 1 also 1 factorial, it remains 1 itself, right? So dp of 1 1, 1 plus 1 minus 1, 1 minus 1 is 0, nothing but 1 is left, 2 into 1 is 2. So here, right? So we are done with the third part, we are done with the third step. Basically the output that we got here is 2, basically dp of 1 1, dp of 2 2, right? So here dp of 1 we got the value 1, dp of 2 we got the value 2 here, right? So here for this factorial remains same, for this one also factorial remains same. So here now let's go with I equals 3. let's do one thing. Let's count explicitly, then match the recurrence, right? In the third step, when we are considering I equals 3. Here we are going with a full permutation window, man. Full permutation window means each of the 6 permutation contributes exactly one internal window of length 3. So this sentence is very important, right? Each of the 6 permutations, whatever permutations we got, 1 2 3 2 3 1, the 6 permutations we got here, right? So I'll show here this one again. So these 6 permutations, right? So here each of the 6 permutations contributes exactly one internal window of length 3, right? So with sum 6, with the sum 6, basically, because with sum 6 means whenever you sum up you will end up 6 itself, because we are going with a permutation one from 1 to 3. One, we are considering the numbers 1 2 and 3. When we sum up uh, any window, when we sum up any window, we have to get the 6 itself. We have to get the sum 6 itself. So factorial of 3, we are considering 6 here. So that gives factorial of 3 6, right? So factorial of 3 we will be considering this one 6. You now you know why we have considered factorial of 3 6. Whenever we sum up within the particular window, we get the solution 6 itself. So we are considering factorial of 3 equals 6 here, right? Simple. Next, let's go with the cross boundary windows here, right? So sliding windows that span the end of one permutation and the start of the next can sum up to 6. Yes, it can, right? So from the enumerated P, the valid starting positions are this one: 1 2 3, 2 3 1, 1 3 2, 7 1 3, and this one 1 3 2 and 2 3 1. 1 2 3, 2 3 1. This one 1 3 2, 2 1 3, and 1 3 2, 2 3 1, right? Starts. So again, from the enumerated P, the valid start positions are 1 2 3 2 3 1 1 3 2, this one 2 1 3 1 3 2 and 2 3 1. So I hope this part is completely clear, man, right? So this is fine. Just give me a second here. Did I miss anything? All right. Yeah, this is fine. Now what I've written here, for one we have written this one 1 2, this one. Okay. Uh, we are going with 3 1 2 1 2 3 and 3 2 1 as well. This one. So basically, I had to show. I didn't show this one, right? I had shown only this part. Starts 1 now 1 2 3 2 3 1 1 3 2, 2 1 3 1 3 2 2 3 1, and this one 3 1 2 1 2 3 and 3 2 1. This of these 6 are full permutation. Starts 1 4 7 10 13 and 16, and 3 are cross boundary. That starts with this one 2 8 14, 2 8 14. So this one we saw. So that is the reason I have given, see here, 1 colon, this one 1 2 3 2 2 3 1 4 1 3 2, 7 2 1 3. So that's what the I have written in theory here, right? Sliding windows that span the end of the one permutation, that span the end of one permutation, uh, and the start of the next can also sum to 6, can also sum to 6, right? From the enumerated P, the valid starting points are, see here, 1 2 1. These are the things that sum up to 6, basically 1 2 4, see here, 7 8, this one 10, then I have given 13 here, this one 3 1 2 1 3, basically it's 13 1 3, this one 1 4 1 6, right? So of these 6 are full permutation that starts 1 4 7 10 13 16, and 3 are cross boundary that starts with 2 8 14, 2 8 14. Total will be we have got 6 full permutations and 3 are cross boundary, right? So we will be going with the full permutations plus cross boundaries, nothing but 6 plus 3. Here in this case we got 9, we got 9, right? So now the recurrence numeric, let's go with the recurrence numeric check here. dp of 3 equals 3 into dp of 2. dp of 2, nothing but we have the value 2 already, we have found, right? So dp of 1 is 1, dp of 2 equals 2, and dp of 3 we are calculating it. So this will be dp of 2 plus factorial of 2 minus 1, accordingly with the formula. So this one n into n factorial, right? So this one will be dp of 2 plus n, not n into n factorial, man. So this one is dp of this one, uh, previous one, dp of 2 plus factorial of previous one minus 1, right? So this one will be dp of 2 plus factorial of 2 minus 1. This will lead to 3 into, so dp of 3, this one 3 we are considering, right? So 3 cross boundary, so this is fine. dp of 3 we are considering n equals 3, this is fine. 3 into n into I plus 1 by 2 we are going with. mm, Here we are going with a factorial 2 minus 1 different one, right? So this is fine, we have went with the same formula for all the things. So this one will be 3 into dp of 2, we got the value 2. Factorial of 2 is also 2, this one minus 1. So this one will be 2 minus 1, we will get 1. 2 plus 1 3, right? So 3 into 3 will lead us to the output 9 here, right? So this 9 is the final answer. This 9 is the final answer basically. So the output that we got here is 9, which is equivalent to the output that they have mentioned for the example 1 within the question. Example 1 within the question, right? So this is confusing as well as this is a bit this thing. The question is easier, but somewhat confusing at the end. This is fine, man. Uh, we got the output 9, right? So, which is equivalent to the output that they have given for the example 1 within the question, or input 1 within the question, right? So, our approach works absolutely correct. Our approach works absolutely correct, right? So, now as we are completely familiar with the approach, let's do one thing. Let's move on with the this one. Final output we got 9, right? So let's move on with the complexities part here. So what will be the time complexity here? The time complexity would be big of n, as we are going with the DP. Basically, we'll be going with a single loop from 2 to n, from 2 to n, right? So each step does big of one work, right? Each step does big of one work. So overall time complexity would lead to big of n. So what will be the space complexity? Space complexity would be big of n as well. We will be making use of the two arrays, nothing but the dp n factorial of size n plus 1, right? So overall time complexity would lead to big of n itself, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n respectively for both, right? Big of n and big of n for both respectively. Now as we are completely familiar with the complexities and approach, we are good to write the code. Let's start writing the code. So now let's start writing the code. I'll just come to the compiler here. So we'll be making use of the fast input and output. So let's import here. I'll just give import Java input output package, right? So this is fine. Next we'll be making use of the different utilities. I'll just import util here dot star. So this is fine. Now let's do one thing. Let me go with the class main here. I'll just go with public class main. This is fine. Within the main class, as they had strictly mentioned in the question, we have to go with the modulo constant, right? So nothing but prime, that is used throughout, right? So let's go with the public here. Just give me a second here. Public, this one will be final in mod equals 9982 44353. So this is fine. This is the value they have given in the question itself, modulo constant, right? So this is fine. Now let me go with the main method. So I'll just give main here. So yeah, this is fine. Now I need here this one, throws exception, mm, or else we'll be getting the error. So I'll just go with throws exception. So this is fine. Now we will be making use of the buffered reader. This is coming from the input output package, right? So buffered reader, I'll just go with br equals new buffered reader new input stream reader of, this is built in, right? System.m. Basically this is coming from the input output package. So this is fine. Now let's go with the print writer as well. So I'll just go with print writer pw equals new print writer. This one will be system dot out. So I hope this is clear, man. So we are just making use of the print writer for the fast output. Nothing but we can just make use of the flush or close at the end, right? Uh, we have solved n number of problems. These things we have to know, man, at any cost. So I have been doing the same from around 2 to 3 years by now. So Java I have been doing since an year, right? So this is fine since 1 year. This one competitive coding. I used to do it with a Node.js basically. So this is fine. Now let's read the n from input. So I'll just go with int n equals uh, integer. This is fine. I'll just go with a percent here. Percent. So this one will be buffered reader dot read line. So this is also fine. The next thing would be, so we have successfully read n from the input. Nothing but the constraint they have given, right? 1 less than or equal to n less than or equal to 1 e6 or 1 into 10 to the power of 6. This is fine. Now let's go with a this one, man. Let's initialize dp array. So I'll just go with long. This is array, right? dp array. So I'll just go with dp equals new long of size n plus 1. Sorry, what did I do here? This one has to be n plus 1 and factorial, nothing but here same thing, new long. This one will be n plus 1 as well, right? So this is also fine. Now we are done with the initialization part. Initially, if you remember the approach, dp of 1, when we considered I equals 1, dp of 1 and this one factorial both remained 1, right? So let me initialize this one directly. dp of 1 equals factorial of 1 equals 1. So the value remains same. All right, so I have initialized 1. This is the base case, right? So now let's go with the iteration part. From 2 we have to consider, right? So we have initialized 1 already. I equals 1 already. So I'll just go with I equals 2, I less than or equal to n. So this one is I plus plus. This is fine. Within the for loop, we have to compute iterated value of the dp and iterated value of the factorial iteratively from smaller I. So I can just write it in this way. We just have to articulate the same thing in the form of code that we had discussed in the approach. So this one will be dp of I equals. So if you remember, we are going with the previous element, nothing but this one will be dp of I minus 1, right? So this is fine, plus factorial of same thing I minus 1. The formula we used in every this one, I equals 1. Within I equals 1 also we use the same, right? Within I equals 2 we use the same, means we within the dp of 3 we went with dp of 2, dp of 2 into this one factorial of 2 minus 1, right? So the previous one we are considering previous value that we got from dp of 2 in when I equals 3, within dp of 3 same thing, dp of I equals dp of I minus 1 plus factorial of I minus 1 minus 1 we did, right? So minus 1, so that minus 1 also we need to consider, right? So this one into I we considered, right? So this is it. And in the question they have strictly mentioned that we have to make use of the mod, right? So let's make use of the mod value. So I have initialized this one to mod itself, right? So this one will be modulo mod, or else we get this one, we get error, man. So let's go with the module mod here, mod value. So this is fine. We are done with, we are almost done. All we have to do is we have to update the factorial, nothing but factorial update. If you remember, I factorial equals I minus 1 factorial into I, right? Again we have to make use of the mod for this one as well. So this one I can write it in this way: iterated value of the factorial equals factorial of I minus 1, this is fine, into I, this one modulo mod. This is fine, man. We are done. Almost we are done with most of the things. So let me do one thing. Uh, we are left with only one thing, nothing but we have to print the final answer, nothing but dp of n modulo mod, right? So I'll just go with, we are going with a print writer, right? So I'll just go with print writer println. So we are going with the dp of n, modulo mod. We can just give here dp of n, so we don't have to make use of the modulo mod. So we have already used this one here and here, right? So we'll get the same, so we don't have to worry about it. So this is fine. Finally, you can just make use of the flush or close along with the pw. So pw is the variable name we have used with the print writer, right? So for this one, to create the instance of the print writer, so this one is fine, pw dot. So instead of the flush, I'll go close. Mm, most of the problems we had made use of the flush, right? So I'll just go with the close for this problem. So this is fine. We are done with the coding part, man. This is it. Simple, right? Very simple. The only thing we have to worry about here is this one. This formula we need to know. dp of I minus 1 plus factorial of I, this one. I minus. So this one has to be 1 as well. I missed 1 here, man. I would have got the error. This is fine. Uh, yeah, minus 1 into I. Right, so this is fine. Before checking the code with different inputs, let me copy the signature starter template here. Just come here, let me paste it over here, right? So let's concentrate on the logical part. Just come to the question, let me copy the input here. So we have to get the output 9. Let's check the same here. Let me run the code. So here what error we are getting? I have not given semicolon here. Let me give the semicolon here. We have the error here. Non-static variable mod cannot be referred from a static context. So see, just give me a second here. Mm, so this one, why I have given public, this one has to be static one. That's what it is screaming actually, right? So let me give you a static. So now this has to work. Let's see. Yeah, this is giving the correct output, right? So 9. This is fine, man. Now let me copy this one. The output that we need to get here is 56. Let's check. Yeah, we are getting the output 56. This is fine. Next, let's go with the input 10 here. The output that we need to get here is 700 at the end, right? So let's check the same here. Yeah, we are getting the correct output, right? So we have made use of the mod value correctly. So now let me do one thing. Let me copy the entire code here. Let me come to the question. Let's get into the submission part, man. Let me hit the submit button. So let's wait for some time. Yeah, now let me copy paste the code here. This is fine. Yeah, let me hit the submit button. I hope this works for all the test cases. Let's see. Let's wait for some time. So you can clearly see here, man, in the toast it is showing accepted, right? Also the verdict that we got here is accepted. So let me open the code here. So whatever the code that we have written works correctly for all the test cases, works correct for all the test cases, right? So I hope the solution part is completely clear. All you have to remember here is this one. So first of all, you have to think this one. Think in the way, in the DP way, basically. We have made use of the DP here. Um, First thing is the value remains 1. We have seen this one in the approach. And the second thing is for loop, and we have to go with this formula basically along with the mod value because it has to stay within the mod value. They have strictly mentioned in the question, right? So this one, these two we have to remember. That's it for this particular question. We are not doing anything extra here, right? So this is n plus 1, n plus 1. I have just went with the n plus 1 for the safer side. That's it, right? All you have to remember is these two formula basically, right? So that is the main thing, right? So this is it for the problem, right? So I hope the solution part is completely clear along with the approach and the complexities, man. For now, this is it. Thanks for watching, guys.